We started here. All right, sample problem 17.7 is going to be a good illustration of all those equations that we just pulled together on our equation sheet for the chapter 17, section 2. Now, let's look at sample problem 17.7. You're going to notice that the illustration on the right should look a little familiar, okay? Because we had actually done sample problem 7.2, which used this very same arrangement that we see here. So let's read the problem statement, and what we'll be able to do is kind of relate back to what we had done in sample problem 17.7 and maybe even use some of that information. We will recalculate it, but I want to just let you know that if you wanted to look back there, there are items, if this looked familiar, that are going to be similar. So we have gear A has a mass of 10 kilograms and a radius of gyration of 200 millimeters. Gear B has a mass of 3 kilograms and a radius of gyration of 80 millimeters. The system is at rest when couple M with a magnitude of 6 Newton meters is applied at gear B. So these gears were considered in sample problem 17.2, as we had just stated. Neglecting friction, determine A, the time required for the angular velocity of gear B to reach 600 RPMs, and the tangential force that B exerts on A. Now, when we did it the first time as sample problem 17.2, our approach was looking at the work energy theorem, okay? This one, we are going to be using the impulse momentum theorem, all right? And a similar thing that we did for the answer here is we wanted to find out what was the force that B was exerting on A. We're going to find that very same force this time using the impulse momentum, and we're going to find that we get the very same answer. So physics, all these things are kind of intertwined, and depending on what you're given and what you're trying to solve will point you in the direction of the approach that you want to take. But some of you, if you start with a different approach, that doesn't mean you're not going to end up in the same place. And we've had that conversation a couple times when some students have said, well, I looked at it this way and I still got the right answer. Totally valid, okay? But since we are looking at angular momentums, we're going to use that to solve this problem in this case. So kind of nice that we can kind of look back and see two different approaches to get the very same answer. All right, so let's first start out just like we always do. We want to identify what we know and then what we want to find and then, where we're going. So sample problem 17.7. Again, this is on page 1226. All right. We know that the mass of gear A is 10 kilograms. We also know that the radius of gyration of A is 200 millimeters, but we need to get that into meters to use it. So this is going to be 0.2 meters. Okay. Its radius of A, okay, it's going to be 250 millimeters, which means that it's going to be 0.25 meters. Mass of B, here B, is 3 kilograms. Its radius of gyration is 80 millimeters or 0.08 meters. And then its radius at B is 100 meters or 100 millimeters or 0.1 meters. Now, what we want to find first the time for B to reach 600 RPMs, okay? This is W2, okay? W1, if you would, is going to be 0. This all starts out with 0, okay? Oh, I forgot to add the moment at B, capital M sub B is 6 Newton meters. Okay. And then B, what we want to find is we want to know what is the force, okay, that is exerted B to A. And so those two things. When we did it the first time in 17.2, we didn't look for the time to get to 600 RPM. We looked for how many rotations to get to 600 RPMs, okay, which is easier to figure out the time as well. All right, so our approach this time, as I said, is going to be the impulse momentum. Okay. Now, we need to identify that up and to the right is positive, but also counterclockwise is going to be positive. So we're using that same convention that we've been using, in statics and such. So we're going to have 3 circles. We're going to look at gear A, and then we're going to look at gear B. Okay. So this first one is going to be our before, during, and after. So we're going to add these two and equal between. The center here, this is again going to be for gear A. So I'm just going to put on the side here, gear A. Now before, okay, before. This is going to have an angular velocity. And we know that before anything happens, the angular velocity is actually 0. So we will, if you would, draw, this would be IAWA1, okay? And this is going to be the center of A. So this is going to be IAW1, A1, if you would, okay? This is 0 because it's starting from rest. Plus, now we know that down here, right about here-ish, okay, this is where we have our contact point with gear B, okay? Gear B is going to push on gear A, and there is going to be a force, okay, right there. This is going to be that force, and it is going to be applied for a certain amount of time. So this is going to be the force, and this is going to be the time, okay? I just don't want it to be confused with that it's a tangent force. This is force times time. It is a tangent force, actually the direction that it's going in, and it's on the periphery, but this is force times time for impulse, okay? And then it's going to be at a radius A, okay? So we're going to have force times time times radius. So the force times the radius is the moment times the time. And we usually see force and time together on an impulse. That's why they're together. So, so it's the moment, force times radius times the time. Okay. And this would be radius A. It's going to be equal to then moment of inertia about A again times WA2. Okay. And that there will be a value. That's going to be after that moment is applied. Okay. Now, we could look back at sample problem 17.2. That was module 3 when we did it. But I'm just going to review here. Let's look at first, what are our moments of inertia? So our moment of inertia for A is going to be equal to mass of A times the radius of gyration at A squared. Okay, so that's going to be equal to 10 kilograms times 0.2 meters squared. Do not use 200 here. So my IA, moment of inertia of A, is going to be 0.4. Okay. Now, the So the moment of inertia for each one of these is A. Now we are going to be, if I remember correctly, let me just go ahead. We are going to be solving for F times T, the actual impulse. All right. So we're going to keep that separate because we don't know those values. We don't know the force and we don't know how much time it's going to take. But we do know what R is, right? So we know RA is equal, actually, I'll put it over here. RA is equal to, and we know that radius to be 0.25 meters. Okay. So that's going to be something that we know. But the value that we need to derive here is going to be the angular velocity at A, okay, after it's gotten to up to speed. So if we recall from this problem, it said that we're going to put this moment on here, and we want to know how much time it takes to get to B, the angular velocity at B, to 600 RPMs, okay? So based on the size of B, we can kind of use that 600 RPMs and kind of go backwards with the velocity ratio to find out what is the rotational speed, then the angular velocity of gear A, okay? So to do that, we first know that we need to get our angular velocity of B into radians per second. So it is at 600 revolutions per minute. So to convert that, we know that there is 2 pi radians in 1 revolution. And in 1 minute, there are 60 seconds. Okay. So WB, minutes cancel, revolutions cancel, seconds do not cancel. So WB, and that's going to be 2 because it's its second, it's like what it speeds up to, should come out to be 62.83 radians per second. Because again, in these equations, we cannot use the RPMs, all right? Now, we're working on gear A. That's gear B. So to determine what gear A is going to be, we need to know what the velocity ratio is, right? So the velocity ratio comes from the size of the 2 gears. So in this case, we can use the radius of B and the radius of A to figure out the velocity ratio. So velocity ratio A to B, it's going to be equal to RA divided by RB. So that's going to be, whether you use the meters or the millimeters, it doesn't really matter here. I'll continue to use the meters. So 0.25 meters divided by 0.1 meters. You could use 250 millimeters over 100 millimeters because they're going to cancel out anyway. So my velocity ratio A to B is equal to 2.5. So what that means to me is that B is going to rotate a full 2.5 revolutions before A goes around once. So it slows down, okay? Now, using that velocity ratio of 2.5, if you recall from our equations, we can now figure out the angular velocity, okay? So, here. So I can say that my velocity ratio A to B is equal to WB2 over WA2. So this is going to be my faster one on top over my slower one on the bottom. And I want to find what WA2 is. So I can say WA2 is going to be equal to WB2 divided by that velocity ratio A to B. Okay. So that's going to be equal to, now we want to use the WB2 that's already in radians that we converted to radians per second. So that's going to be 62.83 radians per second divided by 2.5. So WA2 should come out to be 25.132 radians per second. Okay. Now that's what I need for my equation, okay? So now if I go back to the previous step, I know my WA2, I know my moments of inertia. and I know my radius. So I'm going to solve this equation for the impulse, the force times the time. Okay, I don't know either one of those two, so I'm going to do that. So I'm going to kind of go like this. And I'll rewrite this so that we know what's coming on. If you have it on the same page, you don't have to. Let's look at signs before we get too far. I didn't do it on this one, so I've got to add it back. So this is kind of our basic equation. And if I look here, we know that our angular velocity, we're going to be rotating in this direction. And how do I know that? Well, I know that because if B is rotating counterclockwise, A has to rotate clockwise. When we have two gears in mesh with one another, they go in opposite directions, as we know. So my IA A2 is going to be right there, and it's going to be going clockwise. Now, according to our convention, counterclockwise is positive. So my before is going, I'm assuming clockwise, so that would be negative, but it's 0 anyway. But my after, we know, is going to be going clockwise, so that is going to be negative. So when I look over here, I've got to put a negative out front on my after side, right? Okay, because the angular velocity is going clockwise. Let's look why this one's negative. If we look at the impulse that is going to occur, the force is going to be going down and to the right. If I put my finger on that force, it is going to rotate clockwise as well. So the direction of the moment for A is also going to be negative. So again, this is going to be clockwise. This is going to be clockwise. That's why we have the signs that we do. Okay, now we can put our values in. So we know that this is 0, so I'm not even going to include it. So then this is going to be negative F times T. We don't know force and we don't know the time, so that's going to be something we're going to be solving for. So keep those two together. And we're going to multiply that by the radius at A, which is 0.25 meters. It's going to be equal to, and we're going to take the negative 0.4. That's the moment of inertia of A from the previous step. So if we go back to my first page, my moment of inertia at A was 0.4. And I'm going to multiply that by my WA2 up here. So this is going to be 25.123 radians per second. So solving for FT here, you're going to notice that we have two negatives on either side. They become positive. Divide both sides by the 0.25. My impulse, F times T, is going to be 40.2, and this is going to be newtons times seconds, okay? I put that on the side. So again, this is force times time, not FT like a tangential force. This is force times time. I'm not done with it. So I've got two variables there. Now what I want to do is I want to work on B. Okay, so I'm going to kind of leave A sit there for right now. And I'm going to work on B. Sorry, I got to take a drink here. So gear B. So we're going to do that same thing. We're going to draw our three circles. This is going to be the before plus the impulse during is equal to the after. Now, this time, we're going to use the same convention that we had earlier where counterclockwise is positive. And when we look here, we'll notice that the moment that's going to be pushed onto B is going in a counterclockwise direction. So that means that IBWB1, we know that to be 0, but we'll just assume that same direction. So this is B. And then we also know that the moment, capital M, B, is going to be going counterclockwise as well. On the impact, or on the impulse, though, we have that force that is engaged with A, and it is going to be the F times the time here and the radius distance away. Okay, so this is going to be radius B. And then equal to the after, or again, we know that IB times the angular velocity B2. Okay. So B. Okay, so again, this is going to be our before, during, and after. That's how I like to think of kind of the impulse momentum business. All right, so on the left-hand side here, we know that the total momenta is going to be that moment of inertia of gear B times the angular velocity B1, which we know to be 0. Okay, it's starting from rest. Plus, we have this moment. This moment is going to be on there for a certain amount of time. So we're going to take moment at B times the time. We have to multiply it by the time. And then we're going to subtract F times T times radius B. Now, positives and negatives, remember, we have a moment going around counterclockwise. This is counterclockwise. That's why it's positive. But if we take our finger, we put it on B and we pull in the direction of the force that's going to be on A, it is going to be clockwise. That's why we have the negative there. It's kind of like we're inducing a moment. We're pushing a moment, if you would, or torque through gear B. But we have to overcome A in order to move forward. So it's kind of like, you know, going in that opposite direction, kind of deterring it, if you would. We have to overcome that. It's going to be equal to moment of inertia at B times WB2. Okay. So as far as things that we know the moment at B, we don't know the time. This is going to be an unknown. We don't know the force times time, so we're going to keep that by itself. We do know the radius at B, okay? And we do know the moment of inertia at B, and we do know the WB too, okay? So let's write out what we can. So this is going to be a 0 plus 6. This is Newton meters from the beginning of the problem, times the time, minus. Now, FT, even though we don't know what the force and the time are, remember how up here we have FT is equal to 40.2? That's what we're going to put right here. So this is going to be 40.2 times the radius of B. So from our original problem, our radius of B was 100 millimeters. It's 0.1 meters. Okay, so use the 0.1. Equal to moment of inertia at B. We didn't calculate that yet. Oh, I forgot about that. We didn't. So we need to calculate the moment of inertia at B. So moment of inertia at B, we'll just take a little bit of a detour here. I'll put it down here. IB is going to be equal to, this is going to be mass times, mass of B times the radius of gyration of B squared. So we know that to be, it's the mass of B. Mass of B was 3 kilograms times its radius of gyration of 0.08 meters squared. So IB should come out to be 0.0192. Okay. So we'll just kind of put this in its own little corner. 0.0192. So that's going to be my moment of inertia at B, 0.0192. And then I know the moment of the angular velocity at B2. We took that 600 and we converted it to 62.83 radians per second. Okay. And now our only unknown here is T. Okay. So go ahead and solve for T. We get 0.871 seconds. Awesome, James. Thumbs up. Awesome. Good. Once we get the time, that's part A. Okay. Part B says, what's the force that B exerts on A? All right. Now, if we know that the force times the time is 40.2 Newton seconds, and now we know the time, part B, we're simply going to use F times T is equal to 40.2 Newton seconds. And now using this time here, okay, we're going to divide by 0.871 seconds. Seconds cancel out. We're left with newtons. Our force is going to be 46.15 newtons, which matches exactly the force B on A from sample problem 2. So recalling, I'm just kind of pulling this back up, sample problem 17.2. $46.2, and then for sample problem 17.7, same thing, 46.2 or 46.15. Okay, so 2 different ways of getting to the same answer, a little bit different information given to us and what we were trying to find. In this case, we were trying to find the time, so the impulse momentum kind of made sense to do that. But again, even if you would start in one place, if we wanted to find the time here, and we had solved for the how many rotations B went around to get up to full speed. That's what the question asked here. All we got to do is really convert that to, from RPMs and figure out how much time it would take to do that many revolutions. And we would get the same answer that we see here. Okay. So any questions on sample problem 17.7? Okay. Kind of used those elements that we just talked about and reviewed in our equation sheet. Okay, so now you are ready to finish up the application problems here in Module 5, and there's just a couple at the end of Chapter 17. So what I'm going to do next is we are going to go over kind of an overview of the application problem so that you know kind of what you have coming up, okay? So I'll stop the recording here.